You can do it. You know how to do it, right?
Yeah, give me a second. Okay, can you see?
Yes.
Let me withdraw myself to it's you can see it, right?
Yes. Oh, let's go. The equations are not. Can you stop on the equations?
Can I stop on the what?
Can you stop on the? Can you just go to the slide number 8?
Oh wow, those are Chinese figures. I don't know how the equations got like that.
So when you will be doing next version, please try to make a screenshot of the slide of the whole slide and then paste it back into the PowerPoint.
All right.
When you probably you are preparing slides on one computer and then trying to run it on another one.
All right. Got it. Let me.
Let's do a presentation right now anyway, and if you want, I can show the slides because I have your slides in normal way with equations as they should be. If you want me to.
All right.
Should I project your slides now?
So do my slides have the correct equations, right?
Pardon me? Just
Do my
repeat.
equations?
Huh?
Do my slides have the correct equations?
Yes. I can.
All right. Yeah. Then if you can, project your slides.
Okay. Just a second. Just a second. Okay, you see them?
Yep.
Okay.
Those are the right equations.
Mm-hmm. Okay, let's go.
All right. Hi everyone. My name is Kevin Gima, and I'm studying excited state dynamics in one-dimensional thermoelectric materials. Next slide. All right. So why is hold on just a second. Okay, why is charge transfer important? So in simple terms, charge transfer is simply the movement of electrons from one location to another. So one of the reasons charge transfer is important, and I'm studying it because it's very applicable to semiconductor devices. So we use semiconductors in everyday life, from cell phones to computers to microwaves. So improving their efficiency and their transfer rates could have very beneficial practical applications. Another reason is that studying charge transfer brings us into non-adiabatic dynamics. So in the regular adiabatic approach, uh, where you have the nucleus or nuclear states and the electron with its electronic states. So in the adiabatic approach, we're assuming that the nuclear state has no effect whatsoever on the electronic states or the expectation values from quantum mechanics. However, if we're studying charge transfer, unfortunately, we can't make that adiabatic assumption, and we have to use non-adiabatic dynamics. So in non-adiabatic dynamics, we're assuming that the nuclear states directly affect the electronic states. All right, so that's non-adiabatic dynamics in 2 minutes. All right, and then as stated previously, improving the charge transfer helps improve the efficiency of conductors and semiconductors. So essentially, studying charge transfer helps us improve semiconductors so they conduct electricity better. Okay, next slide. Okay, quick question. So I know you had some complaints about my picture yesterday for photovoltaic process. So is this picture better?
Kevin, please approach closer to the microphone.
Okay. Can you hear me now?
Yeah. Oh, much better.
All right. So is this picture better than the picture I had yesterday for the photovoltaic process?
Yes, but still, you are showing positive and negative charges, but you are not explaining that the semiconductor slide corresponds of P and N doped layers.
All right. So should I get another picture, or should I make that explanation on Monday?
You can look for something, maybe second picture to illustrate this insert. I like the idea of the picture. Oh, no, wait. It shows N-type silicon, this is good. But there is no P-type. I do not see where's the So I do see junction. Oh, probably it was written here, p-type. So it is important to highlight that there is an interface between n-doped and p-doped, alternatively doped layers. That is the key for the whole photovoltaic industry. Okay?
All right, so yeah, I can just put a quick text box next to that arrow and put p-type.
Mm-hmm.
And then with that, I should be able to use this picture then.
Okay, yes, very good.
All right, so.
Just a second. Yes.
Okay.
I'm ready.
Okay, can I continue?
Yes, please do.
Okay. So before I get into the thermodynamic process, I want to quickly contrast that with the previous approaches, which is the photovoltaic process. So in a nutshell, the photovoltaic process is essentially using sunlight or regular light to excite electrons so they move to higher energy states. So here in this picture, we have a solar panel. We have sunlight. It's shining into the panel, and then the photons from the sunlight are exciting the panel. So you see that in the red circle in here, you have your electron flow and your hole, and then to the lower right hand corner, you see you have a junction between your N-type and your B-type. All right. So so that's the photovoltaic process, and you can see that this whole solar panel is used to power a light bulb. All right. So that's the photovoltaic process. Next slide. Okay, so what I'm studying is the thermoelectric effect in lead telluride nanoeffective. It's a thermoelectric effect in lead telluride nano wires. All right. So in this picture, right here, we have a hot side and a cold side. All right. So the electrons are on the hot end. They're absorbing the kinetic energy from the hot end, and then that causes them to diffuse to the cold end. So the electrons at the cold end, when enough of them get gathered there, they form their own electromagnetic field that repels the remaining electrons on the hot end. So you have electrons on the cold end, you have electrons on the hot end, and since you have electrons on both sides, there's a voltage that goes between. And from that, we can create currents. All right. So in panel B, see this whole electric configuration that's being used to make current that's passing that resistor. All right. Next slide.
And please approach closer to the microphone. You disappear from time to time.
All right. Can you hear me better?
Yes.
I'm about as close to my computer as I can be.
Yes. Right now everything is great.
All right. So moving on. I'm studying the thermoelectric effect in lead telluride nanowires. In the past, we researchers have been interested using lead telluride nanowires as a thermoelectric material. So because it's performed great in past experiments, its thermoelectric features are apparent, which is a measure of how well the thermal effect is conducted inside the material is higher than most other materials. So that telluride ones are looked at as a potential thermoelectric material. However, a lot of difficulty has been presented in applying all the research we have done so far in the real world. So actually, like that telluride requires in specific applications, it's challenging. So a lot of
Wait, Kevin, I'm losing the narration. So, what are the features of lead telluride material? Which makes them usable for thermoelectric applications? What are the specific features of the lead telluride?
The specific features of the lead telluride is its conductivity.
Which conductivity?
It's an electrical conductivity.
But it is a semiconductor.
Right. Yeah, I have to research this a bit more by reading past papers, but I'll definitely have a better answer to this by Monday.
Very good. But do you have an idea right now? What is the literature value for the gap of lead telluride?
The literature value?
Yes. If you go to Wikipedia and ask what is the gap of lead telluride?
You mean the band gap?
Yes.
I think at like 300 Kelvin, it's like 1.5 electron volts.
It's what you're talking. It's more about silicon. For lead telluride, it should be substantially less. So
around 4.8 electron volts.
Please try to find it yourself. And one of the criteria for thermoelectric applications is the small gap of the material. So it has sufficiently small gap to be used for thermoelectrics. Maybe you will find some other features as well.
Okay.
Okay, please continue.
All right. So lead telluride nanowires by themselves have negligible charge transfer rates. So by themselves, they're very inapplicable in a lot of semiconductor applications. So that's why a lot of times what researchers do is dope these lead telluride nanowires. So
can I ask?
Yeah, I'm going to ask why. I'm going to explain how doping increases the charge transfer rates, if that's what you're asking about.
Yes, I'm going to listen about it, but the question is how unique this strategy is. Do people dope only lead telluride or any semiconductor? Is it?
They dope any semiconductor,
okay.
Not just lead telluride.
Okay. Yes. Good. Please continue.
All right. So essentially, doping a material increases its electronic properties. So in this case, doping the lead telluride nanowires substantially increases its charge transfer rate. So when we dope them, the charge transfer rate increases significantly, and there's a lot more potential to use these doped nanowires in regular semiconductor devices than undoped nanowires.
Kevin,
All right, can you move on to the next slide?
I have a question.
Sure.
Why nanowires instead of thin films?
Why nanowires instead of thin films?
Yes.
I'm okay. So I'm going to take an educated guess at this. My guess is that it's easier to modify a nanowire's configuration or form with the nanowires. You can add or remove atoms to the process of doping or make any other modifications you need to these nanowires. I'm guessing with these thin films, it's harder to make those modifications. It's harder to add or remove atoms or to otherwise change up thin films electronic properties than it is with the nanowire.
And not only to change, but also to control and monitor the processes. So in thin films, it is easier to monitor the processes. Okay, yeah, good. Keep going.
All right, can you move on to the next slide?
Yes.
Okay, so a quick introduction to doping. So in panel A, we have a regular undoped material. Have your conduction and valence band. They're unchanged. All right, and in B and C, we have two types of doping: we have sodium doping and iodine doping. And the nanowires I'm studying are both sodium doped and iodine doped. All right. So when you're sodium doping, you're removing one band from the valence band as shown in panel B, and then in panel C, you're adding a band to the conduction band. Okay. So let me take a quick digress through the structure of the lead telluride on the nanowire. Can you go to the next slide?
No, just a second. One needs panel D with electronic structure of co-doped model. Please, please consider to add it.
Yeah, I saw that on your slide, but I didn't have time to add it, so I'll definitely add it before Monday.
Okay, good.
All right, can you go to the next slide?
I did. It might...
Okay.
Uh-huh.
So here's my doped nanowire. Here we have a model of my lead telluride nanowire and doped with iodine and sodium. You see here that the pink atoms are iodine and the blue atoms are sodium. Now in a regular lead telluride nanowire, lead has 2 electrons in its valence shell, and telluride needs two orbitals to fill its valence shell. So lead, what happens is that lead donates 2 electrons to telluride, and together they form a nanowire. All right.
Kevin, can you please add your last sentence as a text or as an equation? Because your audience will be mostly physicists who may not understand it. You need it's more chemical feature that you may need to bring up.
Oh wait, you want me to show a chemical equation of how lead and telluride react with each other?
Oh yes, absolutely. Yes, please.
So could I add an equation of Pb2 plus Te 2 minus, and then that equals PbTe. Is that an
Yes,
equation I can add?
yes, yes. It will be very appropriate here.
All right, got it. I'll make it a note of that. Okay, so that's a regular lead telluride nanowire. Now when we're doping with sodium and iodine, because sodium has one extra electron in its valence shell, it's going to replace the lead because they both have extra electron in their outer shell. And then the iodine is going to replace the telluride because iodine and telluride both need electrons to fill their outer shells. So when the sodium donates its extra electron to the iodine, so the sodium acts as the donor, the iodine acts as the recipient. So electron traveling from the sodium to the iodine, that's what's constitute the charge transfer nanowires that I'm studying. Next slide.
Just a second.
Oh, okay.
So the lead telluride has a cubic crystal structure, right?
Yeah.
So you may bring it up and tell what is the typical distance between lead and telluride.
Okay.
And also in your in the slide that you have sent, the aspect ratio was changed, and this makes a deceptive impression that the lattice structure is not cubic. So one needs to keep the proportion of the relative proportion of the bonds and tell that in both y and z direction, distance between nearest atoms is the same.
Okay.
Okay, I'm going to the next slide.
By the way, is this being recorded for me to watch on YouTube later?
Yes. Oh, did you have you seen yesterday recording?
Yeah, I saw some of yesterday's recording.
Okay,
so
good.
I don't know it's there, so I haven't had a chance to go over it yet. So I'm gonna go over both this and this recording by Monday.
Okay, yeah, perfect.
Okay, all right. So these are the various methods and equations that I used to study my doped nanowires. The first method I used was the density functional theory. So we all know that in quantum mechanics, we use the wave function to study our system and to calculate expectation values. Here it's slightly different. So instead of the wave function, we're using charge density. All right. And we use that because they're easier to measure, as said before, these figures than the regular wave function. So I use density functional theory with VASP software to calculate the position and energy expectation values for my nanowires. And then
can I ask something before you go to the second line?
Right. Yeah.
So do you see when I do some marks on the screen?
Yeah, I see it.
Okay, so it is important to put indices because the Kohn-Sham orbitals and Kohn-Sham energies, there are several of them. Like in Schrodinger equation, there are many solutions, right? So I need indices. And there is a very important feature that the density, the potential does depend on electron density in here. One important thing. Another important thing, that this potential, this density does depend on orbitals. And here I'm going to show a very simple equation that you probably know, but I want to bring up to your attention that it is very appropriate here. So density as function of position is summation of orbital I star of R, orbital without star I of R, and summation goes from the first orbital to the highest occupied. So probability distribution or charge density distribution of all occupied orbitals provide the density, and this density determines the potential, and it is a key, and it determines the orbitals. So the density is the key element of the density functional theory. Okay.
All right. So in that arrow, you're multiplying the density by v sub r, the potential.
Not you mean in the Kohn-Sham equation? No.
Yeah. So, or are you saying that the density is a function of the potential?
Density is a function of the potential. Yes, you are right. V of rho and R. So V is functional of the potential. Yes.
All right.
Okay, keep going.
Okay, so then after I calculate all my energy position expectation values with density functional theory and bus, I use my non-adiabatic couplings, which is my to see how my expectation values are. Excuse me. To see how my expectation values are changing with time. Right. So that's that.
So, Kevin, where does the trajectory comes from? So, position of all ions as function of time. Where does the trajectory of all ions as function of time comes from?
The trajectory of all ions as a function of time. They come from the class, right?
Yes, but which how it is computed? Because density functional theory that you introduced one line above is only a theory to find total energies and orbitals at frozen positions of ions. And then in the next line, you are telling that your ions are moving. So why are they moving? How their motion is computed?
the motion may. Hold on, give me a second. The motion is computed from the postcard file in VAS.
Yes, but which in-car is used for getting this motion of ions?
The molecular dynamics in-car.
Yes, excellent. This is perfect. But what is molecular dynamics? What is the principle of molecular dynamics?
Molecular dynamics, as I understand it, it's simply applying Newton's equations in classical mechanics to atoms and molecules.
Super, excellent. But please explicitly tell it in your presentation.
All right.
Good. Keep going.
And then next we have my transition rates, which is essentially how long it takes for an electron to transition from one orbital to the other. All right, so that integral is how we calculate it. And then lastly, we have my density matrix.
Wait, Kevin. Can you please tell how this line number 3 relates to Fermi golden rule?
Okay, so I should talk about the golden rule here. I thought
yes.
I should talk about it when I introduce those red field graphs.
You can briefly mention that this equation is similar, has some connection to Fermi golden rule.
All right.
Okay.
So I should briefly say what Fermi's golden rule is, and say that my transition rate equation here is analogous to that.
Oh yes, would be really appropriate at this point.
All right. Yeah, I'll definitely make a note of that.
Okay.
And then the last equation I have is the density matrix dynamics. The rate of change for that density is equal to the commutator between the Hamiltonian and the density operator plus the transition rate times that density operator. I should make a quick note that even though the densities for this density matrix and the density for density functional theory are similar, they are in fact quite different. So the differences in my case are minor at this point, but I just wanted to make a quick note of that.
Very good, very good. So what's the main difference between this row at the beginning, at the first line, and row at the last line?
This row at the last line is an operator.
Yes, and it does depend on time. So this row is time dependent and is able to describe transition processes. So it's, in some sense, it is transition density.
All right.
Okay.
Next slide.
Oh, before you start, between these two slides, we need one more equation that we were discussing last time, but it is not yet here. We need an equation for this energy of electron as function of time. So we do need a connection between density operator and density matrix, which is the main outcome of your simulation. And then from density matrix, we need to show how the expectation value of electronic energy is computed.
All right. I'll definitely make a note of that.
Do you see what I'm writing?
Yeah, I see it.
Can you explain it yourself?
Okay. So essentially the energy expectation of value as it's changing with time is equal to the sum of the expectation values of energy across all the orbitals. So that's what each n is. N equals 1 is one orbital, n equals 2 is another orbital, and what we're doing is essentially adding the energy expectation values of all those orbitals together.
Okay, and the values of rho sub n density matrix is normalized to 1. So if we just make this summation at any time, it will be equal 1, right?
All right.
So the any element of density matrix is between 0 and 1. And when we multiply the energy by weighting factor, by scaling factor, which is between 0 and 1, each of the energies enter into this expectation value with different proportion.
All right.
Okay, if you agree, please keep going according to your plan.
All right. So the rate of relaxation for my electron in my electron hole, which is essentially the time it takes for the electron in the hole to return to their original state, on one hand can be calculated as the rate of change of my energy expectation values over time. However, the way MATLAB, the MATLAB / non-adiabatic Daniel's code calculated my expectation values was through the integral form you see at the bottom. So MATLAB calculated these relaxation rates by integrating all the energy from 0 to infinity.
Okay.
Next slide.
Just a second, I'm making a comment. Okay. Okay, next slide is here.
Okay, so now that I've discussed the background and methods, I can now get into some of my results. a quick note. I know that I have to double check the widths between these density of states by Monday, so I will definitely do that before Monday.
Okay.
Okay. So the density of state on the left is my undoped nanowire. So that's my nanowire without any doping of sodium or iodine at all. And then on the right is my doped nanowire with both sodium and iodine on here. So if we're comparing these two density of states, what we notice is that the band gap has significantly increased for the doped nanowire. All right, so that's usually a sign that it's that the material's conductivity or charge transfer has increased. So this is a positive sign that doping has worked.
Okay. Would it be correct to say that states at the band gap are contributed by dopants, or the picture is more complicated?
I'd say the states at the band gap are contributed by dopants.
Okay. Good. Next slide. Yes?
Yes. Yes, can you hear me?
Yes, yes.
Okay, here's my absorption spectra for my doped nanowire. Here we see that the electron absorbs the greatest amount of energy when transitioning to orbitals with energies from 1.5 to 2 electron volts. And I just wanted to say, make a quick note that the lowest transition, the number one that you see on the figure there, is dark. This is congruent with the expected results since the electron is transitioning to a higher energy orbital. The absorbed photons show up as a dark transition here because the photons associated with this transition have been absorbed by the electron, and they're not emitted as visible light. So we perfectly expect this transition to be dark. Next slide.
Okay.
Okay, here we see how each of the energies of my different orbitals fluctuates with time. Here we see at time 0 that my band gap is around 1 electron volt. However, as time progresses, the band gap is essentially 0 electron volts. All right. This is due to the following reason. We know that the position of each ion is dependent on time, and then the energy of each orbital is dependent on the nucleus. All right. So this implies that the energy is dependent on time. All right. So this is why my band gap and the energies change with time. This is why the band gap it gradually decreases to 0. All right. So I just wanted to make a quick note of that.
So
next slide.
Would you agree that what is shown is energy of several quantum orbitals as function of time?
Yeah.
You may explain it maybe just as a text, because fluctuation graph is not as common notation. You may just give a little bit more detailed explanation. of what is shown.
Okay. All right. So here we have my red field tensor graphs at the different temperatures, and these graphs show the transition rates between different temperatures. All right. So if we look at the 300 Kelvin graph, we see that the transition rates for orbitals for homo states are very low or very close to zero. But however, the outliers, which is the orbitals far away from homo and nemo, have very high transition rates. However, this changes as the temperature increases. As the temperature increases, the transition rates between all orbitals are very nearly equal to each other. So at higher temperatures, you don't have these outliers. Each transition rate is very close to the average. I just wanted to mention that this finding has been corroborated by our previous a graph which shows how our energy, the energies of GM orbitals are changing with time. So these frequencies to support each other.
Okay.
All right. So let's move on to the next slide. Okay. So these are all the orbitals that I considered in my study. I just wanted to point out how the electron hole orbitals are localized in the sodium dopage. All right, and then I just then for the and then all the electron orbitals are located near the ion. Okay, so I just want to very point that out. Next slide when you're ready. All right, and this is my waterfall graph. On the y-axis, you have my probability density, and on the x and y-axis, you have the energy of my orbitals and the atomic distance of my way. So again, this corroborates what I found in my procedure. All my orbitals are localized near my dopants. All right. So just wanted to quickly point it out. Next slide.
Kevin, we were discussing yesterday that one may need additional equation for illustrating this image, and I'll check if I can bring it up from just a second. So for z-axis, you're explaining it in words here, but it could be reasonable also to give equation and highlight that one performs integration of orbital specific probability density of along x and y and keep only dependence on z.
All right. So I should put that equation here along with this graph.
Yes, yes. I suggest that it will be very reasonable.
Okay. All right. Next slide.
Okay.
Okay. So in these slides, I'm looking at how my chart density distribution is changing with energy. Note that at my lower temperatures, the change for both my electron and my electron hole are almost negligible. So you see flat lines there. However, as the temperature increases, the relaxation occurs quickly. All right.
Mm-hmm.
I just wanted to say that there is one curious trend from these figures. One would expect that the magnitude of the energy difference between the electron and the hole and the temperature would be directly proportional to each other.
Mm-hmm.
However, precisely the opposite happens. As the temperature increases, the energy difference between the electron and the hole decreases. So this is a very curious finding. Then again, there might be human error involved when calculating how my expectation values change with energy. So I may need to double check these figures, particularly the 500 Kelvin and the 700 Kelvin.
Okay.
Next slide. Okay, and then here in this figure, I study how my charge density distribution changes with the with position. Okay.
Mm-hmm.
So two conclusions can be inferred from these graphs. One, all of the charge transfer is localized near the iodine dope.
Hello, hello. Kevin, I do not hear you. You may try to switch microphone on and off, and if it doesn't help, maybe call by Skype. Okay, I'm bringing slides back.
Dropped off, so that's why it happened.
Okay, your slides are on the screen now. I'm on slide 17 with blue figures.
All right, so I'll just start over with this slide. In this slide, we're studying the dynamics of charge density distribution as a function of position. So if you take a qualitative look at this, you know there's two things. One is that all the charge transfer is localized on the iodine dopants. This is what we expect in the doping process. The sodium is the donor, the iodine is the recipient. So the electron from the sodium goes to the iodine. So it makes sense that all of our charge transfer happens near the iodine. The second is that the magnitude of the charge transfer increases with temperature. So you see that as the temperature increases, the electron travels farther and farther distances. So those are two quick things to note from these figures. Next slide.
Yes, I'm on the next slide. Kevin, I'm on the next slide.
Okay, give me a quick second.
Yep.
Okay, next here we're seeing how my relaxation rates are changing with energy. Okay, so we see for the electron relaxation rates that the band gap law, which states that my relaxation rates have an exponential relationship with my energy. We see that the band gap law applies to the electron only at higher temperatures, but there seems to be minimal applicability to the electrons and the transitions at lower temperatures. All right, and then for the electron hole, excuse me, you see that that the band gap law seems to have almost no applicability to the band gap law. All right, so those are the most important findings for this. Next slide.
Okay. I'm on the next slide.
Here we're seeing how my relaxation rates change with temperature. Even if you take a cursory look at this, we immediately see that that the rate of change of my relaxation rate with my temperature is the same, no matter what orbital transition you're looking at. This goes for the electron as well as the electron hole. So in the big gap law, you have an exponential relationship between my relaxation rate and my change in energy, where the relaxation rate is equal to e to the negative alpha, which is a constant, times my change in energy. Now these graphs that you're seeing here looks like a Boltzmann distribution. So what we can infer here that alpha in this case would be 1 over kBT, where kB is the Boltzmann constant times whatever temperature you're looking at. So that's the main finding you have here. Next slide.
Okay. Next slide is here.
Okay, so now to wrap up, we can conclude that doping substantially improves the nanowires charge transfer. So you see a great difference in the charge transfer. There's more charge transfer. We have more control over the semiconductors conductivity, and also we see that the band gap is inversely proportional to temperature. And then I just wanted to make a quick note that we should look at transitions between orbital superpositions in the future. In my specific case, all the orbitals were localized near the orbitals. That's because we were looking at transitions between specific orbitals, specific single orbitals. However, in the future, we should look at transitions between orbital superpositions and see what we find there. All right, and then the band gap law only applies to electrons at higher temperatures. There's almost no applicability to electron holes. And then my electron and electron hole relaxation rates change at the same temperature rate, independent of orbital transition. So no matter what orbital transition you're looking at, the rate of change of my relaxation rate with respect to temperature is the same for each transition. And that concludes my talk. Thank you. Any questions?
Yes. Many thanks. After all of your technical conclusions, what is the impact for industry? Like how your findings can help to improve efficiency or design new technologies? You don't need to be very specific, but just give some attempt of what is your vision.
Okay, so in the past, researchers have had to perform experiments to compute materials band gap. However, if I can prove with my research that the band gap law applies even to some cases, researchers don't have to do these long, complicated experiments. They can just use this band gap law to find the relaxation rates in a short amount of time and do bigger and better things.
Okay. Educationally, which part of this research was most interesting, unusual, and impressive for you personally?
Can you repeat your question?
Which part of the research that you have completed by now was mostly interesting and unusual for you?
I'd say the parts where I saw how the band gap law changed with energy and temperature. It was really interesting to see how the relaxation rates change with these two parameters, and I believe my findings can be applied in the semiconductor industry.
Excellent, perfect. So while we are talking, we were discussing things, and I believe that I hope that recordings will be available and readable, and I will also send you the notes, these slides with brief notes.
I got it. So I'll take a look at this and the previous recording and make as many changes as I can before Monday.
Okay, I do not promise too many effort, but if you send me new version like a couple of days before actual presentation, like on Friday or Saturday, I can go over it privately and develop more comments if you're interested in this.
All right. I'll definitely try and get it done by Saturday then.
Okay. Okay. Very good. Very good. I think we are done. There is another question, technical, not about your slides. Did you hear from seminar coordinator what will be the format of your presentation? Do you need to come in person, or you need to connect by Skype, or did you ask? Do you know how it will be organized?
From what I can tell, it's going to be online. I I'm not coming in person because all classes are canceled. So they're going to try and do this seminar online, like maybe a Skype chat, or like what you're doing now with the nd.gov.edu chat or whatever. So they're trying to work out some online format.
Okay, okay, very good, very good. Do we have anything else to discuss right now?
Not right now. I'll email you if I have more questions.
Okay, very good, very good. And thank you for all your efforts. I see how much work you invest into the project and into the slides.
All right. Thank you very much, Professor. Take care.
Take care, you too. Bye bye.